And here basically I will talk about a new black hole solution for Einstein gravity coupled with the nonlinear electrodynamics and cloud of strings, and we'll discuss their thermal properties as well. So here you see the talk is basically based on my recent paper published in Annals of Physics last year with Dr. D.V. Singh and Dr. Aradhya Shukla, and the title basically is Quasi-normal modes, shadow thermodynamics of black holes coupled with the nonlinear electrodynamics and a cloud of strings. And the DOI for this paper is given here. If anyone is interested to have a full details of the paper, can visit to this link. Okay. So basically my talk is organized as following. So first we will discuss about the gravity model we have considered, and then the solution of the field equation, Einstein field equation for Einstein gravity coupled with the nonlinear electrodynamics and the cloud of strings. And then after getting the new black hole solution, regular solution, we'll discuss the thermal properties, and we'll discuss the stability by calculating the heat capacity, where the signature basically describes the black hole solution is stable or not, or is there any phase transition or not. Okay, and finally we conclude my talk. So let us start my talk by introducing the model. So here you see the Einstein theory of general relativity, known as GR, is one of the most fundamental and successful theory of the theoretical physics. And one of the important aspects of these GR basically is to find the solution of Einstein field equation. And this is a very cumbersome job. It's not a very easy job to find a black hole solution of the field equations. So in literature, actually, there are the two famous black hole solutions are for field equations, Schwarzschild black hole and a Ratner-Nordenstam black hole. So these two solutions are different in the sense that these Schwarzschild black hole solution are the vacuum solution. However, this Ratner-Nordenstam black hole solution is not a vacuum solution, rather it is a solution coupled with a matter. Okay, and these two spherically symmetric solutions have a central singularity which is separated by a boundary known as an event horizon. Okay, so but not all the black hole solutions are the singular solution, but rather there are non-singular solutions also exist for the field equations, and that is known as the regular black holes. And regular black holes, if you see, is described by the Penrose diagram. If you see, or any of Riemannian scalar, if you calculate, that will not blows up when r tending to 0. Okay, so these are the motivation of black hole solutions. And now you see the Maxwell. Now we come to the interaction part and the source part, not a pure gravity part. So Maxwell electrodynamics is basically one of the important interaction of the gravity. And you see the linearity of the Maxwell electrodynamics basically breaks at high energy and due to interaction with the other physical field. So we actually require rather general electrodynamics, which basically explains the theory at high energy as well. And in such circumstances, most suitable alternative is a nonlinear electrodynamics. That is basically as a simplified phenomenological description of these interactions. And this should be such that at a certain limit, if you consider, then it will lead to the Maxwell electrodynamics. And the properties of the nonlinear electrodynamics can be lucid from the perspective of the gravity, since strong vector fields are dominant at the center of black holes. So this is important to consider the Maxwell the nonlinear electrodynamics in the context of black holes. Okay, and the behavior of charged particle basically is described basically by nonlinear electrodynamics around the black holes, because the energy there is very high. So this is a possible consideration for nonlinear electrodynamics as a source term for the GR. Okay, and now we come to the another source term first proposed by Letellier in 1979 as a cloud of strings. That is a model analogous to the pressureless perfect fluid. And the cloud of string is also considered as a source term for the in the background of black hole, because the strings are basically fundamental constituent of the universe rather than the point-like particles. Okay, so one cannot ignore strings basically in the context of black hole solution. So this actually derives us to study the black hole solution in the presence of cloud of strings as well. So together we consider as a nonlinear electrodynamics and this cloud of strings for GR. Okay, and this cloud of strings basically described by the Nambu-Goto action written of this form. Okay, so the action for the cloud of string is given here, where this m basically the mass of strings, and this gamma is basically determinant of the induced metric, and this lambda naught and lambda 1 are basically time-like and space-like local coordinates. Okay, so now we move to a complete action for our theory. So here what you see, this theory has Einstein gravity described by this Ricci scalar, and this curly LF is basically Lagrangian corresponding to the nonlinear electrodynamics, and this is a action for Nambu-Goto action that correspond to the cloud of strings. So here you see that the explicit form of this nonlinear electrodynamics Lagrangian is given like this, and this particular form is considered first time by this paper published in PRD in 2018 by Ghosh, Singh and Maharaj, and they have considered first time this form of the Lagrangian density for nonlinear electrodynamics. And here you see this curly F is basically Maxwell scalar, that is F mu nu, and this K is basically defined as the ratio of square of charge to the double of mass. And here this K basically you can see is in exponential. So this basically gives the nonlinearity, and if you put this K equal to 0, you will have your original, you will receive your original Maxwell electrodynamics. So this K can be considered as a deviation parameter. Okay, so this is actually action of the model, and now we can consider to the solution corresponding to the field equation corresponding to this action. Now we have not written the field equations, but that is mentioned in the paper. So now we directly come to the solution of the field equation. So this solution, the regular black hole solution of that field equation corresponding to the above action is of this form. So here you see that your metric function is given here, where this contains parameter A that corresponding to the CS parameter, cloud of string parameter, and this K is a deviation parameter from the Maxwell electrodynamics, and this M is a basically integration constant corresponding to the black hole mass. Okay, so your metric function is described by 3 parameters, especially M, K, and A. Okay, and now to study the behavior of the metric function, if you plot the potential, so potential is of this form for a metric function for these black hole solutions, and we see the effect of the CS parameter here by changing the values of CS parameter A by fixing the deviation parameter. Okay, so the CS parameter, if you increase the value, you see the metric function potentials becomes more negative and have smaller values. However, if you fix the CS parameter and change the values of, increase the values of deviation parameter, so here you see that for larger k, that is a green, described by the green line. So that is a smaller value of potential. Okay, so for a metric function. So basically increasing the value of k decreases the value of potential and metric function. However, the increasing value of a increases the value of potential. So you can see the nature of a and k on this black hole solution is opposite. Okay, so this is basically description for the black hole solution, regular black hole solution. And now we come to the thermodynamics, because we have very limited time. So I'm not going to much detail about the horizon structures of the model and all these things. That is given in the paper in much details. Okay, so now we come to the thermal properties of the black hole solution. So first thing to describe black hole is by mass, and this mass is basically can be calculated by putting the horizon condition that a metric function is 0 at the horizon, and using this condition we'll calculate the form of m. So the mass of black hole appears like this. Here if you see, if you change you can take a limit for vanishing a, it will reduce to the black hole, the regular black hole solution, to the Schwarzschild solutions. So this is a more general than that Schwarzschild solutions here due to nonlinearity and the cloud of strings. Okay, so here this is a mass, and the Hawking temperature can be calculated through the area law. And area, if you calculate through area law, the Hawking temperature also is described by this parameter k and a, that is a deviation parameter and the cloud of string parameter. So the temperature is also more general form than the Schwarzschild black hole. And you see, we admit that black hole solutions and the thermodynamics basically satisfies the first law of thermodynamics. So by considering that, we calculate the entropy of the model. And entropy, basically, if you calculate using the first law of thermodynamics, it appears like this, where you see this part is an extra piece there. So this is the entropy, temperature, and mass satisfying the first law of thermodynamics. And now you see, we basically cross-check the expression of Hawking temperature calculated from the first law of thermodynamics and through the area law. So that we can justify that our black hole solution basically satisfies the first law of thermodynamics, conventional first law of thermodynamics or not. So here, if you calculate temperature, the Hawking temperature using the first law of thermodynamics, it appears of this form. And here you see this part is an extra piece there in the temperature, rather calculated in the through the area law. So it means that our black hole solution does not satisfy the conventional first law of thermodynamics, because your temperature calculated from the first law of thermodynamics here has an extra piece calculated through the area law. Okay, so this was basically first seen by this paper, the classical quantum gravity, that regular solution basically satisfies the modified form of the first law. Okay, so that modification basically depends on the general structure of the energy momentum tensor. So here you see, if you calculate the modified first law, so modified first law is described by this term, where this piece is an extra piece appears in the total energy part, and this basically J is defined in terms of the energy momentum tensor. So this T naught is a basically energy density. So this particular form can be calculated through this expression, and in our case, this part gives you explicitly that exponential part through the nonlinearity. So this part is appearing here as a nonlinear piece. So if when you plug these values of J here, so your modified first law of thermodynamics becomes this part and dm equal to tds. And this is using this first law thermodynamics, if you calculate the entropy, so it will simply appears as a pi r square, that satisfies the basically area law. So this is so we can say that our black hole solution satisfied a modified first law. And now we come to the study stability and the phase transition. So the stability basically described by the specific heat and their signature, that if your specific heat has positive signature, signifies that a black hole is stable. However, the negative signature satisfies black hole is unstable. So here, if you calculate here the black hole heat capacity, it appears of this form. And now this expression cannot be simply says that gives a positive heat capacity or not until you plot it. So now heat capacity, we plot this expression in terms of the horizon radius. So here, if you plot that expression, appears like this. So here what you see that this heat capacity is a negative also valued and the positive valued, and there is a point where this becomes infinite. Okay, so one can see that for this reason, the negative reason black holes are unstable, and for this reason there is a stable. So there is a phase transition occurs. The second order phase transition occurs at the point is called at the critical radius. We call it the critical radius. So for the critical radius, here you see the values of critical radius here. So there are multiple phase transition occur corresponding to the different k value, deviation parameter. So here you see that here only your black hole goes from unstable to stable region after this critical radius. So this is a point here I should mention, and because of lack of time, I think we should stop here, and we should thank you all for your kind attention. Okay, so for discussion, if we will have time, we can anyone can ask a question. Anyone can ask a
Okay, thank you, Sudhaker. It was very nice presentation. Do we have any questions to this, Sudhaker?
Yes, of course. I'm not sure whether I heard correctly. It says to Professor Sudhaker. Can you hear me? Hello?
Professor Sudhaker, are you here? I think he was disconnected somehow. Dear Mas, could you type it to the chat board maybe once he connected? He can follow the question.
Let me check.
Yes, I think it's the time to say thank you once more to Professor Dr. Sudhaker Upadhyay. And it is the time to pass to the next speaker. So I would like to also leave my chairmanship to the Professor Behnam Professor.
Okay, thank you. Is that have to leave us, and so I will continue. Ali Dehqani, Dr. Ali Dehqani, please start. Sorry, we can't hear you.